tutorial is the second part of the Exam 3 review for Chem 111 at Purdue North Central. In this review, we will be focusing primarily on the electrons. So let's begin the discussion with electron configurations. When we're looking at electron configurations, there's a couple of different parts that we need to look at. One is the principal shell. This is referring to the energy level. And it's also referring to the distance away from the nucleus it is. So 1 would be the closest at the first energy level, and 7 would be the furthest away. S, P, D, and F is the probability of finding an electron in a specific space. And these tend to form shapes. For instance, S tends to be spherical. P tends to be dumbbell shape. D tends to be a clover. It's like two dumbbells that are overlapping. And F is like two clovers overlapping. So when we're looking at that, here's one clover, and then you'd have another one right on top of it. So there's actually 8 lobes there. It's very highly possible that you'll have to be able to explain on the test what the N means and what these letters mean, meaning what shape they're in and how far away from the center of the nucleus it is. Now, when I was a beginning student, I learned that there was 2 different ways of determining electron configurations. One was looking at the periodic table and being able to identify its location on the periodic table and relating it to the electron configurations. The way that made more sense in my mind was something called the Aufbau chart. So for instance here, you would make a list of all the subshells, or all the principal shells. So 1, 2, 3, 4, 5, 6, 7. As I stated before, that's telling me how far away the electron is from the nucleus. So 1 is the closest, 7 is the furthest away. So because 1 is the closest, it's the smallest, it can only afford to have 1 subshell in there, and that's just S. 2 is a little bit bigger, so it's going to have 2S and 2P. 3 is a little bit bigger, so 3S, 3P, 3D. 4 is a little bit bigger, 4S, 4P, 4D, 4F, 5S, 5P, 5D, 5F, 6S, 6P, 6D, 6F, and 7S, 7P, 7D, 7F. Now these down here aren't used because there's not enough electrons and not enough atoms to be able to hold that many electrons. But I keep them there just for my own purposes. You don't have to write them there, and you'll see that in the next chart. As we look at the shapes, so S is a sphere, P is a little bit bigger with two parts, D is a little bit bigger with 4 parts, F is the biggest with 8 parts. The bigger it is, as you go S, P, D, and F, the more electrons it can hold. So for instance, S can hold 2 electrons. So S will always hold up to 2 electrons. It will never be more than 2. So it can hold 1, or it could be empty, but it cannot hold 3. P, 6 is the maximum. So 3S2, 3P6, 3D10 is the maximum for D. 2, 6, 10, 14 is the maximum for F. And we fill those in all the way down. Keep in mind, that when you're filling it in for the electron configurations, you don't just go from left to right like I just did. What you'll do instead is you'll angle it down and to the left, like that. So when you're filling in the electrons, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, we go to 4s2 and then back up to 3d10. So 3d10, 4p6, 5s2, back up to 4d10, 5p6, 5p6, 7p, 7s2, and so on and so forth. So it angles back. I think I should skip one, but that's okay. You'll see it in the next chart. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, so on and so forth. I definitely skipped one in the last one, but you can see the chart here. All the s's have 2's as a maximum. All the p's have 6's as a maximum. All the d's have 10 as a maximum. Notice once you get to the bottom row, they stop filling in the DFs and the 6 Fs and the 7 Ds. They stop there because those are never used. Alright, so how you do electron configurations. First, you want to find the element on the periodic table. It's right here. You'll see two numbers on the periodic table. One is the atomic number. It tells you the number of protons. Not the number of electrons technically, but the number of protons. The bottom number, the number that's not the whole number, that's the atomic weight. Okay, that's not what we're dealing with the electron configurations. So when you're looking at electron configurations, you're looking for the single whole number. Alright, so I said technically with the protons and the electrons. Well, in a neutral atom, for instance here, there's no positive or negative here. So that means the charge is 0. That means the protons and the electrons have to cancel out. They have to be the same. So if the atomic number is 10 or is 11, that means that there's 11 protons. That also means that there's 11 electrons. So that means we're going to fill in the alphabet chart from the top down until we get to 11. So 1s2, 2s2, 2p6, that gives me 10. 3s is next. I only need one more, so it's going to be 3s1. You can do this shorthand by looking at the periodic table. Here's 11. The one right before it is 10, which is neon. You put the noble gas in a box, so Ne, and put the valence electron, the outermost electron, on the outside. That should be a 1. Alright, so notice here it says Na plus. That means it has a positive charge. So charge is equal to the protons minus the electrons. So if the charge is a positive 1 and the protons we know is 11, that means electrons, we have to lose an electron. So instead of 11 here, we're going to have 10 electrons. So 1s2, 2s2, 2p6. I only have 10, and here I go. I'm done. The abbreviation for that would just be this, with no valence electrons on the outside. Fluorine is here. It's 9. There's no charge, so that means they have to be equal. 1s2, 2s2, 2p, there's 2, 4, 5 more would make 9. You could do an abbreviation, but it really won't help you any, because you're still writing the same amount. But I put helium there because that was the previous valency or previous noble gas. If it's minus, that means we're going to add an electron. So that means, once again, I'm back to 10 electrons. These two are going to be identical. They're both going to have 6 electrons, or they're both going to have 10 electrons there. They're isoelectronic. So if it's positive, you subtract from the atomic number. If it's negative, you're going to add to the atomic number to figure out how many electrons you have. One more thing, when you're looking at the electron configurations, we said that S is 2, P's are 6, D's are 10s. If they're asking you for how much an energy level is, let's say they're asking for 4, energy level 4, how many electrons are in there? You would just add 2 plus 6 plus 10 plus 14. You add it across. Because in that subshell, in that shell, that furthest away, the 4th energy level away from the nucleus, that's how many electrons that can hold. Alright, so let's move on to bonding. So we have 2 different kinds of bonding. We have covalent and ionic. Covalent is molecular, meaning that you have nonmetal and nonmetal. And those electrons are being shared. Ionic is a cation and an anion combined. A cation becomes positive, and anion is a negative charge substance. And the attraction between the positive and the negative is what is keeping those two things together. How you can remember this? Cats have paws, so cations are positive. Covalent, we have 2 different kinds of covalent. We have polar and nonpolar covalent. Remember, covalent means that the electrons are being shared. Polar covalent means that the electrons are being shared unevenly. Nonpolar covalent means they are even. They're playing nice. They're sharing nicely. The octet rule, if we go back to the Aufbau principle, the octet rule is indicating that the s orbitals and the p orbitals, so s and p, are all filled up. So that's 2 and 6. That's where we get the octet from. So that means that there's 8 electrons around the atom. There are 2 atoms that don't obey the octet rule, and that's hydrogen and helium. Because if we look at the periodic table, hydrogen's here, it only has 1 electron, while the helium only has 2. It's only going to stay in the 1s region. It doesn't have enough electrons to go out to the p's. And ionization energy is the energy it takes to remove an electron from an atom. And if we go back here to the periodic table again, it takes a lot of energy to remove electrons from this area, from the nonmetals, which is why they tend to be more negative, because they want to gain electrons, they don't want to lose them. Whereas the metals over here tend to want to be positive. So the ionization energy actually increases as you get closer to fluorine. Alright, so let's try some Lewis structures. Let's do an ionic compound first. We have sodium chloride. Sodium is here, chlorine is here. Notice we have a metal bonded to a nonmetal, which means we have a cation and an anion, which means the metal is going to give up its electrons to the nonmetal. So originally sodium has 1 electron and chlorine has 7. This 1 electron is going to be given up to chlorine. So that means sodium no longer has an electron and it has a positive charge. The chlorine now has, instead of 7, it now has 8 electrons. And as I said, it has a -1 charge. Let's take a look at the VSEPR model and the Lewis structures. So we have carbon tetrachloride. Let's do the Lewis structure first. Whenever you're trying to figure out the molecular geometry or VSEPR, you always want to do the Lewis structures first. So carbon is here. You know how many electrons it has on the valence shell by what row it's in. So 1, 2, 3, 4, 5, 6, 7, 8. Once again, that's how we get the octet. Carbon has 4. There's only 1 carbon here. Chlorine is here. It has 7. And we have 4 chlorines. So we have a total of 32 electrons in this compound. So from here, take the least electronegative element and you put it in the middle. So carbon is the furthest away from fluorine, so it's going to be in the middle, and then you surround it with the other ones. So I have 4 chlorines to surround it with, and we connect them. Each connection is 2 electrons. So 2, 4, 6, 8 electrons. Sorry. It should be 24. Sorry. All right. So we have 24 electrons left. So then we're going to pair it around. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24. If I had any extras, they would go in carbon. Make sure everything obeys the octet. Chlorine here has 6 lone pairs, or 3 sets of lone pairs, which is 6 electrons, and then 2 from the bond, so that's 8. Carbon has 4 bonds. Each bond is 2 electrons, so that's 8. So everybody obeys the octet. So here we go. For the molecular geometry, we have, looking at the center atom, we have 4 things coming off of it and no lone pairs. So here we have 4 electron sets and no lone pairs. That gives me tetrahedral. If this chlorine wasn't there and it was an electron, we had a lone pair there instead, we would still have 4 sets of electrons, but we would have trigonal pyramidal instead. If another one of these were gone and we had 2 sets of lone pairs, we'd have bent. So when we see groups here, groups could be lone pairs as well. All right, let's try another one. Ni3, so we have nitrogen and iodine. We have 1 nitrogen and 3 iodine. 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen is in the 5th row, so we have 5. Iodine is in the 7th row, so we have 21. Combine that and we have 26. The least electronegative is nitrogen. Another way to look at this is the one with the most amount of single electrons. Not the most amount of electrons, the most amount of single electrons if you were to do it as a puzzle piece. So we have nitrogen, iodine, iodine, iodine. That's 2, 4, 6 electrons here. We have 20 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We still have 2 electrons left. Let's make sure that iodine has its octets. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So iodine is set. We still have 2 electrons, so they go on the central atom on the nitrogen. If we look at the molecular geometry, this counts as an electron area. So 1, 2, 3, 4 for electron areas. 4. We do have one lone pair, and that takes me to trigonal pyramidal. So when it's asking for molecular geometry, it would be trigonal pyramidal. And that is your quick review of the electrons for exam 3.